so section 13.7 is about the divergence theorem. And this is going to be another way that we convert between different types of integrals. And the purpose of this one is to convert between surface integrals and volume integrals. And the statement of the theorem is this. So if you're thinking about some surface integral, and we'll discuss the details of it after this, then you can convert it into a triple integral over a corresponding region of your divergence, del dot f. And so all the different pieces here are that you're going to be thinking about a closed surface. So when we talked about Stokes' theorem, we were thinking about open surfaces. This theorem is only for closed surfaces. And this is just a generic surface integral. Well, actually, let's call this part that we're thinking about a generic surface integral. But it's going to have your normal vector oriented outwards. And that part's really important. And then what you're doing is you're converting it to a volume integral where the region R is volume inside surface. This is just your divergence that we learned how to calculate a few sections ago. You might also see it with the notation div f. I like to use the del dot f notation because that tells you how to evaluate it. And then you can set up your triple integral in any coordinate system you like. The only thing is if you use like spherical or cylindrical, your divergence, you know how to compute in Cartesian coordinates, so you'll just have to convert everything after you fill in this middle part. And we'll see some examples where we do that. Just to draw a picture of what we're talking about though, here's our bad XYZ coordinates. So here's a closed surface. So imagine that's a 3D surface. It can be filled up. Actually, let's do a surface that you will actually be able to imagine filled up. Okay, here is a sphere. Kind of. So that's a closed surface, a sphere. And it has to be oriented outwards. So I'll just write sphere. There. Oriented outwards means that the normal vectors have to point out of the surface. This would be oriented inwards if the arrows point towards the inside of the sphere. And then the volume over which you're integrating this whole thing is just going to be if you fill up the inside of the sphere all the way. So instead of trying to integrate over the outside of the surface some random vector f, you're going to compute its divergence, and then inside the surface, you set up your regular 3D integral. The one hiccup here is that f has to be continuous. That's really not going to matter for you in this class because we won't try to use the divergence theorem on things that aren't continuous. But if you all do like electricity and magnetism, that tends to be something where you end up with non-continuous F, like you put a little point source somewhere inside your surface and it breaks everything. So divergence theorem is only going to work when you can basically not be dividing by zero anywhere. We're going to go ahead and write out the steps to use the divergence theorem right now, because they should go quicker than the other steps we've been talking about recently. So you have to be given some surface integral problem. You could be well, I'm going to write the steps surface to volume. Technically, you could use it to convert from volume back to surface, but I think this integral is easier than this integral almost always. So you'll usually be going this direction. So you're given some surface integral. And you just need to check that your surface is closed. So that means no open sides, no like curves that define the boundary of your surface. If you see those things, you know that this is a Stokes theorem problem. And if you want to get in the practice, you could check if F is continuous. Just make sure you're not dividing by zero anywhere, or taking funny square roots of things. And then you're going to compute del dot F, the divergence of your vector field F from right here, that F. And then you're going to set up your bounds of integration R for volume inside the surface. And again, you can pick any coordinates you want. And then after you do that, you have a triple integral with bounds set up. You have del dot F is going to give you a scalar function. And so you can just evaluate this triple integral using what we learned back during your prior exam. If you picked anything that's not Cartesian coordinates, make sure to convert del dot F, this thing inside, before you start trying to integrate x's and y's with respect to rhos and thetas and whatnot. And then at the very end, check that your S was outward oriented. Inward orientation changes sign of surface integrals. So this whole approach is computing this quantity for an outward oriented normal vector. After you've done all these steps, just make sure your normal vector was outward oriented. If it's not, you've just been computing the negative of what you're supposed to. So just swap a sign and you'll be okay. And so we'll go ahead and do some examples in this section.